Good afternoon. Our sixth lesson, analytical geometry for you. I'm Evan Snyman from 1.15 making a difference. Today we're looking at the equation of tangents with analytical geometry. And so again, what I've always enjoyed about analytical geometry is how we are pairing ordinary geometry with analytical geometry. So the key idea here with a tangent is if we go to Euclidean geometry, was that a tangent was always perpendicular to the radius. So we know that the tangent will be perpendicular to the radius. What we know from analytical geometry is that if I therefore knew the gradient of the radius, I would be able to find a link to the gradient of the tangent. And that is that these things are negative reciprocals, or that mr times mt equals -1. As I've told you in the previous slide, I prefer doing it using the idea of a negative reciprocal, doing it a little bit more intuitively. Okay, so what we're going to do now is look at an example. As I said, this is going to be quite a short lesson. It's just putting two different ideas from two different concepts together. I might make up pull in another example depending on time. Let's have a look. Okay, so again, reading from our diagram. Okay, we've got a circle centered at the origin. X squared plus y squared equals 20. In this regard, they've made the circle quite straightforward. The tangent PRS has the equation a half x plus k. We can see that. And we can see that PRS cuts the x-axis at t and at s. Yes, determine giving reasons the equation of OR in the form y equals mx plus c. Okay, so again, as you said, we know that because we've got a radius and a tangent, that these lines are perpendicular. And that's going to be the key to this. So 4.1, we know that the gradient of the tangent is a half. Therefore, we know that the gradient of OR, the radius, will be -2/1, or simply -2. We're going to substitute in a point, and again, it's actually kind of confusing in some ways, but in actual fact, the only point that we have that lies on OR is the point of the origin, which is 0, 0. So we've got something in the point 0, 0, the only point we know that lies on this line. We now know that 0 equals -2 times 0 plus c, so 0 equals c, so we've got y equals -2x plus 0. Now I'm hoping, I really am hoping, that a large number of you guys are shouting at the screen saying, well, of course the y-intercept was going to be 0. We could see that the y-intercept was going to be 0, so you've done a whole lot of work for no reason. And again, if you did spot that earlier on, I would like to compliment you. It was quite clear from the diagram that the y-cut of OR was going to be 0. As a result, to determine the coordinates of R, well, R is a point of intersection, so we're going to make these two things equal each other. So -2x is going to equal a half x plus k. But now hold on, we don't know the coordinates of k yet. So this method would be a bad method. So again, what I hope I'm role modeling to you here is, again, don't just jump in and write things down because you know that R is the point of intersection, and therefore point of intersection must be where the two lines equal each other. We don't know k yet, so that method won't work. What we can do is we can substitute this idea into the circle. And so we know that not only is it the intersection of the radius and the tangent, but R is actually the place where it is the intersection of the line, the radius, and the circle itself. So we now therefore know that x squared plus -2x squared equals 20. We've got 5x squared equals 20. X squared equals 4. So x equals plus or -2. Again, following on, therefore the x value at R is 2. We can substitute that in. As a result, y at R is going to equal -2 times 2 equals 4. And so the coordinates of r are going to be 2 and minus 4. I'm hoping you realize that because this thing is symmetrical, we can realize that therefore the coordinates of v will be minus 2 and positive 4. Okay, determine the area of OTS. So now they're asking us to do something quite different and quite unusual. They're asking us here to find the coordinates, the um, the the area of this triangle. So that's a little bit unusual. Okay, I haven't seen that too often in my teaching career. 4.3. However, what I do need to have is I need to have a length and a breadth. Sorry, a area, a base and a height. So area of a triangle is half base times height. And so what I'm going to choose to do is I'm going to choose to try and work out what the coordinates of k are. K. So I now know that I can find the equation of this line PS. So y of PS is going to be a half of x plus k, and I have the point 2 and minus 4 lying on this graph. So I now have that minus 4 equals a half of 2 plus k, and so as a result, half of 2 is 1, bring it across, and so I've got minus 5 equals k, so y equals a half x minus 5, and as a result, point S, to find an x cut, we make y naught, so S will be the point 0 and 10. Now, I'm choosing to do this because there is a very clever way to do this question, which is based on the coordinate system rather than based on your geometrical notion of a right-angled triangle. So what I can do here is, instead of using the idea of what I'm going to mark here in yellow, of using this right angle here and saying, well, therefore, that side of the triangle could be the height, and that side of the triangle could be the base, and then doing half base times height, and that method will work perfectly fine. So for 4.3, I could do that quite comfortably. Okay, I could do that the length of OR will be the square root of 2 squared plus minus 4 squared equals the square root of 20. The length of SR will be the change in x squared. So the change in x is, sorry, the change in x, I've done it the wrong way around there in the previous one. I'll do apologize. The change in x here is, again, I hope you guys are screaming at the screen because it's not 0 and 10, it is 10 and 0. Let me come back here and fix this as best as I can. Do apologize. Okay, so again, just please, again, I know it's not great. Please, I hope that you can see that it is very easy to make careless errors in this topic. Okay, the change in x is going to be 8. The change in y is still going to be 4. So we've got 64 plus 16, which is the square root of 80. So we can say, therefore, that the area will be a half of root 20 times root 80, which will be equal to a half of the square root of 1600, which is going to be a half of 40, which is going to equal 20 units squared. Now, there's nothing wrong with doing it that method, and again, if that's the method that you followed, please feel free to use it. However, I'm going to choose to look at it slightly differently. And what I would like you to realize is that part of why we do coordinate geometry is so that we have the coordinates, the axes, to our advantage. So instead of using the yellow, the right angle of the tangent and the radius as our right angle, and instead of focusing on that right angle, what I'm going to choose to do is I'm going to choose to focus on just the idea of why did they give it to me on a set of axes. And the key idea which I'd like to focus on here is this idea that the base could be the x-axis, and the height would then simply be the y value to r. As a result, the base here would be 10, the height here would be 4, and my area would be a half of the base times the height, which would give me 20 units squared, a lot easier than I had in the yellow example. Okay, be that as it may, we can now move on to question 4, 4.4, and again, you could go and work out. Okay, so we went and worked out V using symmetry earlier. We can need to work out the value of T, but we actually do know the value of T because T would come directly from knowing our Y cut, and our Y cut just now was -5. So we know that from 4.3, following on from 4.3, we know that therefore the T value is going to be 0 and -5. The V value we had from symmetry just now, which was -2 and 4. And so therefore the length of VT would be the change in x squared, excuse me, plus the change in y squared, the square root of that, which in this case would be 4 plus 81, which would be therefore the square root of 85. Okay, as I said, there were some nice tricks in this question. They started out fairly simply with a circle centered at the origin, but that allowed me to get the symmetry, to get V. And so although it was apparently an easier circle, it allowed me to get V using symmetry. That is not quite as easy if the circle was centered off-center. They tried to con us by this idea of the radius being perpendicular to the tangent to find r using those two equations as our point of intersection. But please don't forget that there are actually three graphs that intersect at r, where the graph is a tangent. It's the equation of the radius, the equation of the tangent, but also the equation of the circle itself. And so I would encourage you to have a look at this question and see that although it is in some ways quite friendly and quite easy, there are some quite tricky little nuances to this question, which I think are worth investigating and taking this question seriously. We've got one final lesson coming up shortly, and that is on with more advanced examples. And so I really do encourage you to make sure that you understand this example before we move into the more advanced examples of the next lesson. Thank you very much. All the best.